Okay, so thank you very much for virtually being with you in this workshop. So I'm working with Simone in the adaptive optics team in Arcetri in Florence, and it's a team that has been developing AO system for quite some time now. So this talk is going to be somehow, let's say, overlapping with one of Miska before, but we took care, or let's say, of having different perspective of the same problem, actually. So we are putting the emphasis more on the technological challenges. It's the same topic, but you'll see probably more pictures, let's say, even before, and less equations. So it's split in three parts. First part, of course, is related to large telescope and how we want to get rid of atmospheric turbulence. And then we change, or let's say we step up from the small field AO system to large field AO system. And the last part is about the future system like MAORY, which is the multi-conjugate AO system for the European ELT. Okay. So is a fact. Telescope wants to go big since the very beginning. We have been seeing this constant increase of size of telescope areas, ramping up from Galileo's telescope with a lens of 3 centimeter diameter, up to the current ones that are in the class of 8-10 meter diameter for the mirror, and we have a bunch of them all around the dry places in the world, and to the next ones, which are extremely under several sense. You see there has been an increase of factor 10 to the 6 in collecting areas. So why we do want to go big? Of course, collecting area. A large area means being capable of going fainter. Fainter means more far away, and more far away means older. So it's something, of course, that makes perfectly sense. What is less evident, of course, is that the high angular resolution is also linked to the telescope diameter because of diffraction. So being capable of having a better resolution means being capable of having more details, but also means that being capable of getting a better background rejection. So it's all things that we want, okay? The theoretical diffraction limit for a telescope is lambda over d, where lambda is the observing wavelength and d is the telescope diameter. This is an angle, and is, for the ones of you that are working in microscopy, is very much the same things as spatial resolution in the focal plane, which is linked to the numerical aperture of the objective. Okay, it's the same things, just conjugated to the infinite instead of the focal plane. So it's diffraction limit is an angle for us. The unit is typically the arcseconds, which means 5 microradians, which means being capable of seeing 5 millimeter, resolving 5 millimeter at 1 kilometer, for instance, if you have a resolution of 1 arsec. Just to put some numbers, naked eye means diffraction limit of 20 arsec, so being capable of resolving 1 millimeter at 10 meter distance. Probably the best ones of us can do something like this. And when we go up to large telescope, this resolving power, resolution, theoretical diffraction limit angles is going down a lot to a fraction of an arsecond, a few milliarsecond, which means an incredible resolving power. Okay. Everything would be nice if we wouldn't have the atmosphere between us and the stars. And what you see here, just a couple of examples, looking at the moon or looking at a bright star, and you see actually this fluffy image of a size which is about 1 arsec, no matter what, okay? And this is basically the diffraction limit of a 10 centimeter telescope, and you already see the problem, of course. So this is related to the atmospheric turbulence. Miska has already said a lot of things about that, so I can go quite fast on that. It depends on the heat dissipation inside the air. And for what we need, I mean, today what we need is to know that there is a characteristic parameter that is called R0, which is actually representing the turbulence power, and actually is kind of a coherence length. The larger it is, the better. Let's say the weaker is the turbulence, and over a patch of R0, the wavefront is flat enough to produce good images. Okay. So R0 is about 20 centimeters at visible wavelengths, and it scales as lambda more than linearly. Okay. The overall wavefront RMS is a fraction, is a function of this R0, and accounts to some microns RMS. So the wavefront is not flat; is a corrugated two-dimensional variety with RMS, which is some microns. Okay. Another thing which is related to the R0 is the image size in seeing limited conditions. So when, as in the movie that we have seen before, we look at a star through the atmosphere, we are limited by the seeing, and the star size will be lambda divided by R0, which is more or less 1 arc-second in typical astronomical size. So of course, comparing lambda over R0 to lambda over D, we see that we have a loss of resolution with respect to the theoretical limit, which is in the order of 10 divided by D divided by R0, which is something like 10 to 50 in near infrared wavelengths for current telescope, and it will be even worse, of course, for larger future telescopes. So it's something that is clearly unacceptable. Since we are talking about tomography, we have to keep in mind that okay, turbulence is distributed vertically all through the entire atmospheric columns, and since actually turbulence is generated by heat dissipation, the air is heated by the ground. It makes no surprise the fact that the strongest turbulence layers are close to the ground, and then you see in these graphs the temporal evolution is quite fast. You have layers that appears and disappears a few minutes or hours later on, so it's quite a complex thing. But let's say the constant thing is that strongest layers are close to the ground, and this is actually used by wide field AO systems. Its turbulence is chaotic, but we have some laws, fortunately, and the power spectral density is following Kolmogorov law, which says that actually larger spatial period modes have larger amplitudes, and so I mean you can imagine that you can project the wavefront over a basis of modes of increasing spatial frequency, and you will see that increasing the spatial frequency, the amplitude of the modes will decrease. Okay. So we can look at the same thing at the PSD, not also as a function of the altitude, producing this representation in which every point in the matrix correspond to the power of the turbulence at the given spatial frequency and at a given altitude. This is in the case of the uncompensated turbulence, and then of course you can do, let's say, the integration of these values along the two dimensions to get the overall variance of the turbulence. But you see a distribution of the turbulence in altitude and in spatial frequency. Of course, the whitish, the strongest, which means that the worst offenders are large spatial scale modes close to the ground, okay, which is, of course, the first things that you want to correct. Okay, so having said that, we leave with a telescope of 10 meters or something like that, that could reach image resolution in the order of a millisecond, but because of atmospheric seeing, we obtain the same resolution of a backyard telescope. This, of course, is not well received by astronomers that ask for solutions. One solution is an expensive one, is the one of putting the telescopes in the space, and indeed, we have done it with the Hubble, and we will do it with the JWST, and we got fantastic results for a quite expensive price. The other solution is to try to correct the atmospheric turbulence with ground-based telescope, okay? And this is where AO kicks in. Okay, well, this is just yet another example, a scheme of what AO is doing. Has already been explained by Miska before, so we don't need to go through that again. Is a loop between something sensed by the wavefront sensor and corrected by the deformable mirror to, let's say, correct in the direction of a reference star, the yellow one, while the instrument will observe actually in a slightly different direction, which is the one of a scientific target. This is because actually the scientific target is always too dim to be used as reference star by the AO loop. Okay. So single conjugate AO is a way of doing adaptive optics in which we don't care about the field, basically. So we have a single reference star, we have a single deformable mirror, which is conjugated typically to the telescope pupil, and this means that actually we don't care about tomography. We don't care about where the turbulence is located in the atmosphere. We just kind of collapse all the wavefronts corresponding to the various layers. We collapse them on the pupil, and we apply this deformation on the DM. This will result, of course, in a good correction in the direction of the stars, in less good correction away, and I'll try to explain it in a moment. Okay. The first question that we could ask ourselves is how many actuators are needed to correct the turbulence. Miska already said that the turbulence is moving fast, so we need the mirrors capable of changing shape at millisecond scale. How many actuators? Of course, let's say the pitch of actuators affect the capability of fitting the wavefront with the DM. So when the DM has a pitch of one actuator per R naught, typically the residual wavefront, as shown in the picture, will be so small that the resulting image will be diffraction limited. Okay. Seen in this way means that a SCAO system will be capable of correcting all the frequency scales up to a given precise frequency, which is the one of reachable by the DM, and completely correct all the turbulence at every altitude. So, okay, the residual wavefront, the residual PSD will be the one shown here, completely zeroed up to a given spatial scale. And the residual will only be the part that cannot be fitted by the DM. So it will be greatly reduced, and of course it will produce fantastic results on axis. Okay. And this is actually what a single conjugate AO system is doing. This is an example of the image taken by the SCAO system at LBT compared with the same field done by the Hubble Space Telescope in the space. And you clearly see that the image done by the ground-based telescope with AO system is much sharper because the telescope is larger, so it has a diffraction limited resolution better refractory limited resolution than the HST. So under certain conditions, AO is capable of getting rid of atmospheric turbulence in a very effective way. By the way, AO went mainstream this year because a Nobel Prize was awarded to 3 people studying supermassive black holes at the center of our galaxy. And Reinhard Genzel, which is one of the researchers that won the Nobel Prize, in an interview acknowledged the technological breakthrough of adaptive optics. Okay, so the fact that through adaptive optics you can increase the optical resolution so much, enable to track and measure the position of stars that are orbiting around the black hole with incredible accuracy, and this is what was needed to demonstrate the black hole in the center of the galaxy. Okay, and this is done with, I mean, I would say all the work of this group was done with the AO system of ESO at Paraná. So AO is glamour. But then we are told we are moving to the second part in which this glamour is fading a little bit, because when we want to increase the field, soon problems are arriving. Okay, already in the stupid sketch on the left, you see that actually the yellow light, the one that we are measuring and correcting for, is crossing turbulence, crossing atmosphere on a different path compared to the red light, which is the one that we want to observe. Okay, this is causing a bad correction of turbulence, especially the ones that is located at higher layers, when the lateral shift corresponding to an angle theta on a layer H is big enough that it's comparable with R0. Basically, the correction on that layer is not effective anymore. So the higher you go for a given angle, the less corrected you are. Or if you want, on the contrary, let's say for a given angle, you can go down and having a good correction of a turbulence close to the ground. Okay. So, seen in this way, again, for a scout system, what I show here now is not anymore the power spectral density along a single direction, but is averaged over a given field of view, 5 arc-second, so a tiny field of view on the left, and a larger field of view, 60 arc-second, 1 arc-minute on the right. Okay, in the 5 arc-second field of view case on the left, you still see that the correction is somehow effective. It's not totally black anymore as with a 0 field of view case, but they are still correcting most of the turbulence close to the ground, and somehow also, let's say, most of the turbulence close up to a few kilometers. But if you enlarge the field of view, the correction is becoming extremely weak. I mean, we only correct properly the ground layer where the DM is conjugated, and we basically don't correct at all, leaving the uncompensated turbulence in most of the altitude and in most of the spatial frequency, which means that the resulting image will be bad. Okay. So from glamour, we are quickly turning into kind of a tragedy when we want to go wide. Okay, the field of view of a single conjugate system is small because of an isoplanarism. If you want to correct large field, we cannot compensate anymore in the pupil what we need to compensate the turbulent volume, and this opens 2 issues that are related to measurement and correction, of course. Corrections, ideally, we would need volumetric corrections, but the technology so far is to have mirrors, and only a few of them. We cannot easily squeeze in the system tens of hundreds of mirrors. And for what concern the sensing, we need to do a tomographic measurements, which means looking at the turbulence along several line of sights, which means that we need several reference sources. And this is opening a sky coverage issue. We don't have several natural gas stars close by any target that we want to observe. This is calling for the use of artificial sources, laser gas stars, which are good to solve the sky coverage issue, but they are opening a variety of additional issues. Most of them have already been mentioned by Miska before. So we end up immediately with a system which is really complex. So at least 2 deformable mirrors, at least 3 laser gas stars, at least 3 NGS, natural gas stars. So since, the second week of this work is about experimental challenges, this is clearly an experimental challenge in the field of AO, going for a wide field correction. Multi-conjugate, just to keep on using the same scheme. After the telescope, there is an optical relay which is reimaging given atmospheric layer up to a plane where a compensator, a deformable mirror, is placed. We can put several of them, and of course one of them will be in the ground, because in the ground is where most of the turbulence is. This is the general idea of using a relay to reimage pupil planes after the telescope. First question could be what, in this case, is happening to the turbulent layers that are not conjugated to the DMs. The one conjugated to the DMs will be corrected, but what's happening to the turbulence outside of the conjugated planes? Same thing as before, okay. A layer which is sitting at a given distance delta H from the deformable mirror will be partially compensated, for modes with large spatial period, will be less compensated in the modes with small spatial period, which is shown here is the same, let's say, attempt of measuring a 60 arc-second field, but instead of having a single DM, now we have 3 DMs placed at ground, 7 kilometers and 17 kilometers, for instance, and the 3 DMs have different numbers of actuators in this example. The high layer ones has less actuators than the ground one. In this case, you see that, for instance, the worst offender is residual turbulence in a high layers close to the high layer DM. So in that case, for the 60 arc-second field, one should go in the direction of increasing the number of actuators. But if you want to go wider, even wider, say to 2 arc minutes or 3 arc minutes field of view, immediately the correction is becoming so thin, so concentrated around the conjugated planes that you need more than 3 DMs to effectively correct the turbulent volume. And this is, of course, additionally increasing the complexity. Okay, so there is a relationship between the angle, corrected angle, and the number of mirrors that we need to deploy to correct the volume. Makes no surprise, I would say. In terms of sensing, Mr. already showed that. I took the same picture. Starting from the ground, let's say a few stars are enough to sample effectively the pupil. But as soon as we go higher, the meta pupil is increasing because of the wide field, and so the corrected volume is actually a reverse cone. So the layer is increasing in size, and you end up with part of the meta pupil that are badly sampled or not sampled at all. And so the solution in this case, of course, is to increase the number of guide stars, which is adding again the complexity. And since we cannot find enough bright guide stars in a small area close by the target that we want to observe, we have an issue of sky coverage. Basically, we don't have the possibility of using the system whenever we want to sky. We are limited to a few regions where there is abundance of natural guide stars. This is clearly unacceptable for system of this complexity that wants to be, you know, so workhorses for big telescopes. So we have to overcome the sky coverage limitation, and the solution, of course, is to make use of laser guide stars that are bringing with them a variety of issues that are listed here. Of course, you saw the sky coverage, this is the pro. But in terms of cons, you have tip tilt indetermination, which leads you to force you to use a natural guide star anyhow. And actually, in the case of MCAO, it forces to use free natural guide stars. And then LGS are elongated objects that appear prospectively elongated on the wavefront sensor, and this causes issues in the wavefront sensing design. They are at finite distance, especially, let's say, 90 kilometers is a lot, but you have to imagine, you have to take into account that ELT focal length is 700 meters, so it's really a finite distance, which means that the object position will change with telescope elevation, and then the cone effect. So how the tilt indetermination is particularly, why tilt indetermination is particularly bad for MCAO systems. Imagine you have just focus aberrations conjugated to the ground, so on the ground. You got two wavefront sensors. Both wavefront sensors will measure focus only, and this will be the signal to your system that it has to applying focus on the ground at the end. If instead you have focus at higher altitude, the wavefront sensor, the on-axis wavefront sensor will still measure only focus, but the off-axis wavefront sensor will measure focus and tilt. So it's this additional tilt measured by the off-axis wavefront sensor that will tell the system, okay, this focus that you have measured has to be applied on a high layer DM. So the ratio between focus and tilt is telling the system where in altitude is located the focus to be compensated. But of course, if you have laser guide stars, then your wavefront sensors are not measuring the tilt anymore. And so you end up in both cases with just a measure of focus. So you don't know where to apply the focus that you have measured. And this is causing uncompensation of the plate scale modes. Miska has shown a video before, which is making this image magnification not stable. This is why when you're going laser guide star on a wide field system, on an MCAO system, you cannot use only a single natural guide star, but you need 3 of them to measure tip tilt. So you wanted to solve sky coverage, you solved it, but I mean, you added additional complexity. And of course, in terms of sky coverage, things are getting better because it's true that you still need 3 natural guide stars, but you can use much dimmer natural guide star because now you only need 1 subaperture in the wavefront sensor. You only need to measure tip tilt, so you can use much dimmer stars. And in these conditions, you maybe reach a reasonable sky coverage with a decent technical field size, or most likely the field size of your system will be needed by the technical field more than the corrected scientific field, which is another cons of going wider with AO systems. Okay. So, short, we end up with a system which is extremely complicated, complex. Still, such systems have been done on the 8-meter telescope, like Gemini. GEM system is working on sky with 5 laser guide stars. You see a sketch of the optical bench, but as you see, is quite complex already on an 8-meter telescope class. It's about 2 by 3 meters, and is already 1 ton of instrument. Okay. And on the right, you see that the correction is indeed perfectly nice over a wide 90 arsec field of view. So the last part, what's happening now? We are going even bigger, from very large telescopes to extremely large telescope. The ELT is on its way, is an incredible machine in terms of everything. It has a 40-meter diameter telescope mirror, segmented, an optical design which is a free mirror anastigmat. It embeds a deformable mirror that I think will be explained by Roberto Biasi later on. The numbers are huge, as I was saying before. The equivalent focal length is 700 meters, and the focal plane scale is 3.3 millimeter per arsec. It means that if you want to transmit a field of 150 arsec as we want, you end up with something which is half a meter big size. Okay. On this telescope, MAORY is the multi-conjugate. Will be the multi-conjugate AO relay, and which will provide diffraction limited imaging capabilities to a couple of instruments. One is MCAO, depicted here in the picture, and another one is a future one yet to be selected. We are working on the system, and I mean, you have to compare the scale of this bench with the one of GEMS that I've shown 1 minute ago. It's the same architecture if you want. So there are 3 DMs and 4 plus 2 postfocal DMs here in the bench. A total of 7,000 actuators, 6 laser guide star reference sensors, 3 natural guide star reference sensor, a large patrol field to enable good sky coverage, aiming at correcting a wide 60 arc field. Everything is scaled up in size a lot. Also here in the optical design, you see that we are speaking about 4-7 meters tall, 6 meter depth, and it is a big instrument, 30 tons of mass, mirrors that are in the class of 1 meter. So everything is new for us, is scaling up a lot. And one interesting point is why it's so large. Can't we, produce optical relays that are shrinking down the entire things in an effective way, and enabling us to do an instrument which is much smaller? And apparently it's not so easy. I don't want to say impossible. Apparently it's not so easy. So but first of all, the optical interface, as I'm saying, the entrance focal plane is half a meter diameter. So you need something which is collecting the light on this area. Then another point is related to the demagnification principles. Okay, so if I demagnify the pupil from 40 meter to 100 millimeter, I apply a magnification of 400. The longitudinal magnification will be the square of this number, which means that layers at 0 and 10 kilometer will be collapsed in the image space, and will be spaced at only 60 millimeter apart. And now imagine that if you want to add a couple of deformable mirrors of 100 millimeter size, spaced apart only 60 millimeters, things are becoming tight, and it's not easy to arrange everything in this way. And also, when shrinking the size of the pupils, you to enlarge the angles in such a way that, for instance, in the case of MAORY, if we reduce the pupil size to 100 millimeter, the angles in the optics starts to become about 20 degrees, which means fast optics, a lot of aberration. So the optical design becomes a problem. Apparently, and so this is actually forcing us to stay on wider DMs, on wider pupils, and so on wider optics and wider DMs. One question, fundamental question is, can we go beyond mirrors? So, I mean, to the people working in microscopy, what we want is a deformable volume, not a deformable mirror, something which is capable of acting of 10K actuators, 10,000 actuators fast, very fast, with quite some optical path difference stroke, possibly achromatic. So it's not an easy device. I don't know if it exists currently, probably not, but it's something that we want to explore in the future. Okay, some details about wavefront sensors. Here, I mean, the big point for LGS wavefront sensor, as Miska was saying, is related to the spot elongation, the fact that the prospectical elongation of a sodium layer is huge, and is actually forcing us to compromise the design on several other aspects. In terms of natural gas star wavefront sensor, there the complexity is in enabling the required point instability. Actually, the natural gas star wavefront sensor must be stable at the level of a few microns to enable the point spread function stability that is required to the systems. And of course, this is also a large optomechanical system rotating on top of the instrument. It is not something technologically easy. Final note about the control scheme. Everything has been said in the previous talk. I want to add that the control matrices are very big in these cases, and they are not stable in the sense that they must be continuously recomputed because they are related to the geometry of the footprints of the stars, of the guide stars, crossing the volume, and these footprints are continuously changing when the telescope is following a star in the sky, going up in elevation, culminating the meridian, rotating the telescope, and going down again. So this is adding quite some complexity to the management of the AO system. And of course, it's not only atmospheric turbulence. We have the system is big, and this is causing a lot of additional wavefront error sources that must be corrected. Telescope vibration, phasing of the primary segments. We have very tight optomechanical tolerances that results in collimation issues. We have to maintain stability when the temperature is changing, and of course, this implies some deformation of the optical surfaces. And then, last but not least, also we have light which is traveling inside the dome for hundreds of meters, and this is posing also some issues of internal instrument seeing, not only atmospheric seeing. So I think I've conveyed the idea of how complex is to scale from a single conjugate system to a wide field system, especially the future ones for the extremely large telescope. And so, I mean, conclusion, I mean, when Galileo invented the telescope, actually, he was scaling up the eye size by a factor 5, from a few millimeters to the 37 millimeter of the length of his telescope. And this factor 5 was enough to start an incredible revolution. Now, today, in ground-based astronomy, we are more or less aiming to do a step from 8-meter class telescope to 40-meter class telescope. It's the same factor 5 increase. Hopefully, we will get the same revolution out of this. Thank you.